All right. Welcome, everyone. You're in for a great treat, and literally most of you already got some really great Trojan food. It was a good coincidence that we had that.
Pure chance.
Pure chance, yes. Okay, so this is a IEEE distinguished lecture, and co-sponsored by HDSI, the Halujulu Data Sciences Institute, as well as the Institute for Neural Computation, and several sections of IEEE, and several local CAS, EMBS, ED, all these different local chapters here in San Diego, as well as student chapters here at UC San Diego. Right? So you're in for a great afternoon. We start with a 2-hour tutorial on everything you ever wanted to know about AI, and on a shoestring budget, and that's the key, right? And then we have a lecture on a bit more detail of all this the great technology. That will be at 3:30. But so very much delighted to introduce Jason, and this everyone knows Jason. In fact, everyone who has ever heard about spiking neural networks and has gone one step further, actually doing something with it, which means running some Python or whatever code, right? You all know the SNN Torch tools that Jason put together, been downloaded 200,000 times.
Oh, yeah.
So, and I can go over a whole list of accolades, but well, no, it's fine. So you got the best paper award of the IEEE proceedings, which is an important one. Many other, yes, and Jason Eshraghian is a double distinguished lecturer of IEEE. So I guess double IEEE, what would make is this IEEE or whatever it's like.
So honestly, I'd prefer it if you just went to like the worst language model and asked it to hallucinate a bit about me and just make shit up. That would be ideal.
Well, no. So when we say double, we mean basically there's two societies, CAS and EMBS, right? So it's already distinguished, but there's double distinguished. Is great. And so here today is going to be a CAS distinguished lecture. We'll get you back here for an EMBS distinguished lecture a bit later. So. Without further ado, so Jason, you have the floor. Please regale, entertain us with a great tutorial. So please go first.
Awesome. Thanks, Gert. Yeah, no, thanks so much for the invitation. Thanks, Shashank, Samira, whoever else that organized the Kabob. That's very important to me. That was my one condition to come down here and deliver this. This is a, yeah, I'm not sure if I'm looking forward to hearing myself speak for the next 4 hours. So, oh, Master has granted me with a break. No, but all right, God bless. 3.5 hours is wonderful then. Can't wait. So yeah, the first half is going to be very low level, the 101 of language. And then I guess, latter half is the more research-oriented stuff that my lab does. So with that being said, we are going to, oh, good. Echo. We want to mute ourselves. Excellent. Beautiful. So yeah, quick overview. Next 2 hours are just going to be all about this part one. So yeah, let's do what the average computer scientist does and check in with ChatGPT. So this is an old screen capture from 3.5, but I'll ask it, how much energy did it cost to train you? And ChatGPT ironically wastes a bunch of tokens telling me everything that I didn't ask for. So it gives me a few potential reasons for high energy consumption, hardware that runs these models. That is one of the major keys. It refers to model size, data set size. That's all well and good. Those will definitely have an influence. But the reason it refused to give me the answer is that much of this information is proprietary. Tech analysts have attempted to reverse engineer the cost. So let's do a little bit of a pop quiz, right? How much do you think it costs to operate ChatGPT, both for usage or inference and for training? So any rough guesses, or anyone already know an order of magnitude answer? Say it again.
Yeah.
200 million for training. Yeah, roughly right there. Yeah. Do we know how much it costs per day for inference to serve all you people that can't write research papers anymore? Me too.
About the same or?
About the same.
No.
Not quite the same, right? But it's estimated that serving over 1 billion queries per day costs OpenAI like 1 million per day, just order of magnitude, right? Whereas training a model like GPT-4 is estimated to approach and potentially exceed 100 million. So historically, we were really concerned about training. But now the LLMs are kind of treated as a bit of a commodity. Everyone is using them. We have a single model serving an internet-wide spectrum of users. Inference has suddenly become a major concern again. So let's try and understand what it is that leads to such a high cost. Part one, the next, Jesus Christ, 2 hours are going to be something about modern language models. We'll spend most of the time on just the 101 basics, the very basics. These are not exploratory strategies. These are common approaches that are well researched. They're out there in deployment. So this really is more of a tutorial. And then once we have that grounded, then part two will be where I start talking about my lab's research and all the weird shit that we've done. Hopefully everyone can be on the same page as a result of that. So the more weird techniques that they're all borrowing principles from the brain to make LLMs more efficient. So yeah, without further ado, let's grind. Let's talk about LLMs 101. Feel free to interrupt at any point. Just make this as casual conversational as you wish. So the objective of a language model is to predict the next token. And so by training a large model in this way, we accidentally end up with LLMs that appear to understand a lot more than we would have initially expected. So more concretely, the input to a language model is a sequence, and the output is the next item in that sequence. This is repeated again and again until you end up with entire sentences, PDF files, a therapist, whatever else you might use chat for. And loosely speaking, this process is known as autoregression, where the next value of a variable is predicted based on past values. Doesn't have to be language. It can be the stock market. It can be the weather forecast, whatever. But let's focus on language for obvious reasons. So I take an input sequence, the cat in the, and then I feed it to my neural net. A well-trained model might return hat, but unfortunately, I'm not rich enough to afford many GPUs. So instead, my model returns hostage negotiation. Now, as intelligent as cats might be, this is probably not the next correct token. But nonetheless, we append hostage negotiation to the input and repeat the process. So we've got the cat demanding 12 laser pointers, and this sounds somewhat plausible. I'm not sure why there's this big ass red cross here, but we repeat this until we hit some end of sentence or end of text token that tells our model your job is done. Let's clear that output, try again with a well-trained model. This time we get the more stereotypical Dr. Seuss response, the cat in the hat sat on the mat. Again, I prefer the laser pointer example, but now we have a more conventional sentence. So what if your model gets something wrong? Now, when humans get something wrong, we might correct each other. And during training, we do something called teacher forcing, where the model's output, if it doesn't match what my data set says, then you're effectively forcing it back to the correct answer, and you append the correct answer, the correct token to your input. So my goal right now is, again, to explain the 101 of an LLM, but perhaps at three distinct, I guess, phases. First, your input, your output, and most of our time is going to be on the transformations that take place between them, or otherwise the brain of a model. Let's start with the input. So having said all of this, there are two lies that I have fed you all so far. Firstly, neural nets operate on numbers, not words, right? And
You talk about predicting the next word. However, in the way we construct sentences as humans, we don't think of the level of words, but we think of the level of clauses.
Yep.
Where a word comes together with adjectives, with prefixes, with prepositions, and things like that. So how is it that just predicting the next word actually comes up with these level clauses?
Yep. So the reality is that we don't even predict the next words with language models, right? We're predicting the next tokens. In the next 2 minutes, I'll probably cover that to some degree, but people have swept across this space of predicting the next character over to predicting the next, I guess, multitude of words in a speculative fashion as well. So that entire spectrum has been I don't want to say exhausted, but people have done research and there is no concrete answer on what works best, just a bunch of trade-offs. Testing, 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 testing poorly. Do you want me to just scream a bit louder? It is what it is. How are we up at the back? Can you hear me? Cool. Okay, so neural nets work on numbers, right? And secondly, they're not necessarily words, right? They can be parts of words, characters, symbols. So more generally, they are known as tokens, and the process of breaking up, I guess, these strings into smaller pieces is known as tokenization. So my example sentence is not actually generated one word at a time. It most certainly could be, right? I can do that, but your language model has the flexibility of, it has more flexibility if the sentence is broken up into perhaps a more fine-grained vocabulary. It is possible to take this to an extreme and have one character generated at a time. And back in the era of recurrent neural nets, that was incredibly common. But if I take my favorite book, then this means I need to run inference on my language model 30,000 times, and then you'll obviously run into memory problems if every, I guess, character is treated independently, both in terms of physical memory and model memory. Whereas we can reduce that down closer to, say, 10,000 if we were to 10,000 steps if we use GPT-2's tokenizer, right? So now that we have our sentences broken up into manageable pieces, we need to turn them into numbers. Each word in your vocabulary is going to come from, it's going to come with what's called an embedding, right? That is a vectorized representation of tokens. So our first word is represented by a vector, as is the second word, and so on and so forth. So it is really these numbers that are going to be passed to your neural network rather than the word itself. And this kind of begs the question, do these numbers have meaning, right? To gain a bit of intuition, I'm actually going to adapt an example from Grant Sanderson from 3 Blue 1 Brown. He did a beautiful job of explaining it. There's no point fixing it, so thank you, Grant. Let's reduce our dimensionality to just 2 elements, right? So that we can visualize it cleanly on a set of Cartesian coordinates. And let's say that we have numbers for the word uncle, right? 0.25 on the x-axis and 0.5 on the y-axis. And let's do the same for the word auntie, right? Got 1 vector for uncle, 1 vector for auntie. And what this might imply is that by moving a concept, say delta 0.25 units along the x-axis, that might correspond to a change in gender. Now take the embedding for another word, say king. What word do you think we would arrive at if we moved 0.25 units to the right? It would be very reasonable to estimate and guess the word queen, right? But I'm going to go ahead and tell you that perhaps we've missed the mark on this one. And queen falls a little bit further away from that point. And that's totally plausible because queen could mean Lizzie, it could mean Queen the band, it could be a chess piece, it could be Queen Bee, it could be the other Queen Bee, it could be Yas Queen, and my personal favorite, it could be Queen Elizabeth Yas Queening. But otherwise, this type of relationship really holds true. My point is, if we want to be able to, I guess, capture the richness of what queen could possibly mean, then you might need more dimensions, right? So 2 dimensions, not going to cut it. In addition to that, if I was to put queen into a sentence, then you might appreciate that like all of these words, all of these other words in the sentence could very well influence where this embedding vector lands. So an LLM is going to use its surrounding context to influence other words and make their embedding more precise as a result. So queen on its own will still have an embedding that is ambiguous. So what I'm showing you is how an LLM might modify this vector. Now, bringing back our, and we're going to go into the nuts and bolts of how surrounding tokens are going to influence every other token when we get to the brain of the model. Bringing back our original sentence where each token sits in a higher dimensional space, this somewhat implies the existence of this huge, gigantic matrix that does the job of converting words into numbers, and it can very much be treated like a lookup table, right? If that token is there, then just pluck out this vector of numbers and feed that to my network. And there are plenty of pre-trained tokenizers out there. For example, this shows the first and final 3 token embeddings of GPT-2 before OpenAI closed up access to their models. And these are their actual honest to goodness values rounded to 2 decimal places. And what's kind of nice is that this matrix can be accessed in just 2 lines of code, and you're able to transplant it into your own architecture. And I think most deep learning folk don't question this too much. They leave other people that have more compute to kind of train those tokenizers for them. But perhaps more interestingly, what are the dimensions of this matrix? On the x-axis, there are close to 50K different possible tokens in the vocabulary. These include punctuation, random words, pieces of words, and the end of text token at the very end. On the y-axis, we have the dimension of each embedding. I showed you a picture of a 2-dimensional case. In practice, for GPT-2 at least, you've got something more like 768 dimensions. Now, if you want a deeper intuition behind what all of these dimensions could be getting at, I would strongly recommend the deep learning series by 3 Blue 1 Brown on YouTube. But again, at a high level, these vectors all point into a space that then, I guess, pertains to some sort of concept and how concepts are related to one another. Now, if you had a lookup table with every single word, including plurals and hyphenated words, across every language, then you'd end up with a gigantic dictionary. The x-axis would very much explode, right? But this, if you had a lookup table with every character instead of every possible word, then the x-axis would then shrink significantly, but at the cost of a model that needs more memory and more computation by iterating through every single character. So you can already start to see a bit of a trade-off. So this matrix refers again to GPT-2, but modern language models have a lot of variation. GPT-3 and DeepSeek both have something like 100,000 entries in their vocabulary. Llama 4 goes beyond 200K. You can probably appreciate that if you want a model that speaks in other languages, in particular languages with a lot of characters, such as Chinese, then your model absolutely needs a gigantic vocabulary. The size of each embedding varies a lot as well, from 1K to 7K. And there are studies of what the optimal point might be, but I think that the honest truth is it does feel quite inconclusive. It seems like 7K is probably a little bit overkill, and it is possible to get away with smaller sizes while allocating computation elsewhere.
These numbers are for vocabularies in English or including all languages?
All languages. DeepSeek absolutely has a ton of Chinese characters in its vocabulary. There's Korean, every language. Everything together, yeah, exactly.
Yes, some procedures for this one, because in order to make a calculation of the probability, you need to take it from the.
Yep, the number of training samples, the number of training tokens nowadays seems to go beyond 45 trillion. Yep.
For this one, for 5,000 vocal value.
Say that again, sorry?
For 5,000 vocal value votes.
For 5,000?
Yeah,
I couldn't tell you.
50,000.
50,000? Sure. I mean, the more tokens you have to train on, the better your model does. If you want something that's state of the art, then yeah, you got to go into that tens of trillion case.
I clarify that trade-off here was it's just computation, the variable. That's the only negative for you.
No, not quite. Because if you were to be able to process it, so the question was, what's the trade-off at the if you were to have a vocabulary at the character level? So sure, you would need more computations because now you're spitting out every single character one at a time, right? Painful. But then on top of that, you need a model that has really damn good memory because you have so many more steps. And you need to be able to project way back into the past to be able to start generating any sort of correlation between words. Say I plug in Harry Potter into my model. How many characters are in Harry Potter? Am I going to remember the first character I plugged in after I don't even know the order of magnitude of characters in that book, but would I remember it by the time I reach the end of the book? Absolutely not, right? The context windows of modern language models are 100K. Dr. Seuss, 30,000 characters. Yeah. Any other questions? Excellent. So keep it coming. I'll probably also not know a bunch of shit as well, but that's fine. So I don't think we know where the optimal point is, and that's okay. Things work. Now, as a matter of interest, someone wrote a tool that can also see all of ChatGPT's available tokens here as well. I'm not sure if it's been updated since 2023. You can kind of see the first batch are all symbols, then we see suffixes, entire words, subwords, and just a lot of interesting stuff. It's cool to dig in and see what's the backbone of this tool that everyone's become so dependent on. The final tokens are mostly, I guess, signals to the language model. We also have a few random words like Icelandic, merciless, daycare. I don't know. I don't know why this is the order, and it probably doesn't matter. Point is, we know how to go from words to numbers. That covers the input to an LLM. How do we go in the other direction, from numbers to words? You've done all your processing, which we'll get to. Let's look at the output. So what does it mean for the model to predict the word hat, right? It's obviously going to be some numerical format. And with a vocab size of 50K, it stands to reason that the output of the model will be a vector of the same size. Each entry corresponds to one of 50K tokens. The value corresponds to the probability of the token coming next in the sequence. So you can interpret this output vector as a probability distribution. Let's pretend like each entry corresponds to a word. A well-trained model will sample the word hat 99% of the time and hostage negotiation 1% of the time, right? But sometimes you might try saying the same thing to ChatGPT and it gives you different answers, right? That's because you're able to modify a parameter known as temperature. So changing the temperature can smooth out that distribution. So let's see what I mean. Here, the temperature parameter set to 0 keeps things solid and deterministic. You more or less know what you'll get, the distribution that you'll get every time. Increasing the temperature somewhat arbitrarily to say 1, t equals 1, will start to bring a little bit of uniformity across that distribution. Going up to 2 will keep pushing for uniformity. It'll lead to some more creative outputs, but in practice, this t equals 2 is the highest that ChatGPT will let you go through the API, and it's just modulating a softmax function if you care. It's probably the case that OpenAI have kind of set that t equals 2 limit because they don't want excessively weird or randomized outputs. They want some sort of boundary condition there. Now, taking it to an extreme where, say, temperature is 20, that might lead to something like this. So you can see the distribution becoming, it just gets more uniform, right? And at some point, you will reach nonsensical outputs as a result. Again, in practice, you're changing how the softmax function is applied to the output of your LLM. The softmax implying that it's not a hard max, right? So rather than zeros and ones, where 1 corresponds to the maximum value, softmax is, you're amplifying the larger signals and crushing your smaller signals, right? Increasing temperature just kind of reduces that amplification factor. Now, taking it to an extreme, so we've seen that extreme. And with that covered, it's time to, I guess, get into the meat of it, right? The brain of a stereotypical language model. I think a lot of people have seen this image or PDF at some point in the past 8 years. But back in 2017, a team from Google Brain uploaded this very inconspicuous paper to arXiv. They proposed the transformer architecture, and it's undergone some changes in the past 8 years. But there are a set of core operations that have survived all this time.
Sorry, kind of going back to the last slide, 9 question. So the output, you said it's a sampling based thing.
Yeah.
So what I'm wondering is if it's like a softmax or a logits, then at the end of the day you do like a winner take all anyway. So is it really sampling or
you do what?
So if at the end you have a softmax over the logits, you will anyway do a winner take all to predict the next token, or is it like you sample with the probability that the softmax gives you?
The latter. Okay. Yeah, you sample with the probability that the softmax gives you. So even with t equals 0, t equals 0 or t equals 1, then you will have a deterministic distribution, but it's still a distribution because you're going to sample from it. Yeah, good point. Good point. For the longest time, I actually misinterpreted and thought it was indeed a winner take all, right? Yeah, I'm sure that works. It's just probably a less interesting language model. So prior to 2017, prior to this guy, language modeling was generally done via recurrent networks or a mixture of recurrence and other attention mechanisms, or even via 1D convolutions that are kind of scanning through your sequence. So this paper didn't propose attention, but rather it found a way to remove all other architecture types from the attention structure in doing some sort of meaningful language processing. So this is the architecture they propose. You can see two sort of pathways here. On the left is what's known as an encoder to compress inputs into a vector. On the right is a decoder, which does a bunch of operations and then generates your probability distribution of what the next token might be. Nowadays, all prominent language models can generally be interpreted as a single input-output transformation or a decoder-only architecture. The naming is, in my opinion, a little bit misleading because the first step still involves some sort of input embedding where text is turned into vectors. So the nomenclature doesn't really matter too much to me. Moving forward, I'm going to break down this decoder-only architecture and use GPT-3 as the representative example of language models. But just know that other LLMs, modern LLMs that are out there in deployment, follow a very similar set of operations as well. So this is where we get kind of nitty-gritty and my attempt at maximizing animation tools in PowerPoint. It's pretty fucking hard. Take the input, the cat in the, as our canonical example. Each word is represented by a vector. In GPT-3, the vector size is 12K. This is a big number. It might be a little bit more efficient to compress that down into a smaller space. So every single one of these tokens is fed to 3 fully connected layers, or MLPs, or dense layers, or linear layers, whatever. And this generates 3 vectors named the query, the key, and value for each token. Every single token has one of these vectors. And they're also squeezed down into this 128-dimensional space from 12K. We now apply a dot product of every query vector with every value vector. So we sweep across the query, what we're going to do is sweep across the query and key. Yeah, did I say value? My bad. Queries and keys. Fuck. Yeah, whatever, just what the slide deck says. So we're going to sweep across the queries on the x-axis of this matrix, Q1, Q2, Q3, corresponding to the cat in the. And then we're going to sweep across the keys, thank you, Gert, on the y-axis. And likewise, they also correspond to the cat in the. And we're going to take that dot product of everything with everything else. So Q1 to Q4 encodes the tokens, the cat in the. K1 to K4 does a different encoding of the same sentence. And we're taking the dot product of every embedding with every other embedding. All this tells us is how related is each word with every other word. And that's going to
be showed off with both. So it's 1 key and 1 query per token.
Correct. 1 query, 1 key per token. In a moment, this does generalize to multi-head attention. Excellent. We're going to dig into that a bit as well. Good. So, no, I'm glad you're forecasting what's going to come. I think it's good to catch me as well, just so that people are not misled if they're to miss something in the future as well. So keep that coming. How related is every token with every other token? This will all evaluate. This is a Hadamard, a dot product. You're going to get a scalar value out of all of these. So I've swapped out the clunky vectors with circles that represent how large the numbers might be. And note this particular large value. So this query relates to cat, and it links it to the key in, right? 2 and 3, indexes of 2 and 3. The model understands that the cat must be situated in something. So in the machine learning lingo, we say that the key in attends to the query cat. Now we normalize every value by dividing it by the square root of the embedding dimension D, which helps with numerical stability. That doesn't matter, don't worry about it. And then the softmax operator is applied to everything column-wise. As a refresher, the softmax function turns a list of numbers into a probability distribution. It raises every value to E. Then it divides that value by the sum of all exponents in that list. And the resulting effect is this. Large values are amplified, while small values along the column are squeezed smaller, approaching 0. And mind my beautiful animations, this is done for every column, ensuring that each one of these columns adds up to 1. Let's go back and replace these with numbers. And indeed, this is a bit contrived, but every column does add to 1. So when training a model, we want to take advantage of 2 things here. So 1, the abundance of data, and 2, the parallelism of GPUs. So when we have a sentence such as the cat in the hat sat on the mat, then there are effectively 8 next token predictions that we can kind of milk from that, right? There is a risk here, right? If I was to do a next token prediction for every single word, then there is a risk. In this matrix, Q is asking which of few tokens is tightly related to me. So we kind of need to null out or zero out all future values of K on the lower diagonal. And doing that at this stage would mean that the columns don't add up to 1, and we would no longer have a probability distribution. The fix is kind of trivial. Before applying softmax, we apply what is known as a causal mask, and we scale those bottom lower diagonal values by -infinity. If you multiply these 2 matrices together element-wise, then you apply softmax. After that, you'll end up with something like this. Your attention matrix looks like this. Every element tells you how much one token influences another token while accounting for causality. But how do we go from this guy to predicting the next most probable token? So a neural network is just a chain of operations or transformations. So I think a better way of thinking about this is to ask, how do we transform our current tokens into the distribution over the next possible tokens? So really, the goal is to transform our original 12K dimensional embeddings, hence the name transformer. In the next sequence of steps, the thing you should be thinking about is, how do we use this attention matrix to take these 12K tokens on the left and instill within them some sense of surrounding context, right? An understanding of the words that they're adjacent to, or tokens. So this attention matrix and the original tokens need to interact somehow, right? Remember that queen example? I want to know which queen I'm talking about, right? These vectors on their own don't do that for me. I need to be able to update those tokens to give me a bit of insight. And they do this via the value vectors, right? We've taken the dot product of queries and keys, but the values have just kind of chilled out in the background there. And I'm just showing the 3rd column for now, but Q3 corresponds to the word in, the notion that something is inside of something else. And K2 corresponds to, I guess, cat, right? So every element in this column is zeroed out except for, I guess, V2, the second value vector related to cat. And so all of these get summed together, but really V1, V3, and V4 are all zeroed out, or at least close enough. Softmax isn't perfectly zeroing things out. And so we end up with a 128-dimensional vector that might add the notion of cat, of a cat being situated inside of something else, right? And I'm going to call this vector delta E, and it comes from the 3rd column. And the same thing is done to every other column. Many of these vectors are removed or suppressed by the many zeros before being summed. And the purpose of these delta E vectors is to, again, instill the input tokens with a sense of their surrounding tokens, but they're totally different dimensions, right? These guys are all 128 dimensional, whereas the inputs are 12K. To make these dimensions match, the dumbest thing that we could possibly do is to pass these models through another MLP layer, converting that into something 12K dimensional, and I'm going to call that delta E dash, and that's incredibly convenient. I now have a vector that tells me how much to change the original embeddings by to provide them with information about their surrounding words, and not to mention they're the same size. So perhaps they could just very naively be added to one another, right? So we add delta E dash to our original embeddings. You do it for the first embedding, you do it for all other embeddings. Very good, congratulations, you've just mastered attention. To summarize, QK transpose created this initial matrix, right? This numerator is just QK transpose. I've represented it with all these dot products. It's just QK transpose. And then you scaled it by the embedding dimension, applied a columnized softmax along with a causal mask, and then the value vectors were distributed across the matrix, right? V1, V2, V3, V4. These are all added up columnized to give us delta E. That is added to the original embedding after an upward projection. There are a couple of things missing here: positional embeddings and multi-head attention. Multi-head attention is really quite straightforward. Everything enclosed in this dashed box here is repeated in parallel. So in the case of GPT-3, there are 96 heads. That means 96 QKV matrices, 96 unique attention matrices, 96 unique upward projections back into the 12K dimensions, but the various delta E dash vectors are all going to be summed together. There are some models that concatenate them all together, and then the upward projection puts it into the dimension that you need. So not a hard and fast rule for them to naively be added, but they all work. So the idea is that each attention head, each of these parallel processes, might learn additional relationships, which becomes important as sentences become more complex and as words can kind of retain additional meaning. But wait, so there is still more, right? We haven't finished attention yet, or transformers yet. There isn't too much more. The rest is just like a sequence of mind-numbing steps. Each of these transformed embeddings that have been, added together, they go through two more MLPs. So one upward projection into a space that is 4 times the embedding dimension for GPT-3. These might change model to model, followed by a nonlinearity, a downward projection back to 12K dimensions, a residual connection, a layer normalization, fucking whatever. And then as far as GPT-3 is concerned, repeat that 96 times, right? And then once that's done, you go through the unembedding phase to obtain the word hat, right? 1 token. And then you circle back in a loop and repeat everything again and again and again and again, right? So what changes? Yeah.
Right, just a question about the word choice. So when you have these keys and values and queries that were extracted, what are they optimized for? Like, how are they 3 different things from the same? Or what do you mean by the words? Like, do they give you an intuition?
So it's the intuition I gave, the best possible intuition I gave was just that because it is quite abstract, right? I mean, it comes from the origins of QKV come from search algorithms where you have a query, and then you look up for like you look up a particular key in order to obtain a particular value. That is like, I guess, the reason why those things are named the way that they are, right? Query up here is like, yo, what's good? What do I care about? The keys say me, care about me. You find a correlation between the two or an anti-correlation. Then you scale that correlation by the value, right? After softmax and all that.
Sure. Follow. These W's, they're all pre-trained, right?
Where am I looking?
WQ, WK, WP, WP2, WP, all these are pre-trained, right? They're fixed models.
Depends on what your goal is. Yeah.
For this, they are.
Sure. Yeah.
And so one head attention thing is just one shot through and then it gives you the word.
Yep.
But if it's 96, then there's 96 options.
There are 96 separate delta E dashes, and the delta E dash 1 is going to be added to the output of delta E dash 1 from the other head, and 96 times for each one of these vectors. So each of these heads is kind of nudging your, I guess, token embedding into a direction that it now accounts for additional context
And the alpha is just one distribution over the
across the column. Yeah,
across the entire on this set of columns.
right. Yes. Johannes?
Yeah, just to add to this point, like the analogy to certain algorithms, I think what helped me as an analogy is to just think of content addressable memory directly. Because really, if you replace the softmax with a hardmax, then you take the query and you find the best matching key, which the content addressable memory would just be the index of the row, and then you multiply that with whatever vector you have stored in that memory there, which is the key vector. So it's one-to-one the same, right? It's just here as a softmax. It's not a
Right.
hard.
And so with that being said, I'd like to invite Johannes to come and give the rest of this lecture because I wouldn't mind chilling out for a bit. So everyone around us, mush up. So yeah, with that being said, what changes on the second pass through, right? We did all of that work for one bloody token, right? What changes next? And you might be able to appreciate, right? When you type into ChatGPT, the process of typing a bunch of words and then hitting enter, the computations might be slightly different to when ChatGPT is then churning and generating the next tokens that follow, right? We'll get to a little bit more detail in a second. Now, on the second pass through, we have the next word ready. So let's make space for hat, and we chain the new embedding for hat back to the input, and this will go through the same process as before. It's passed through the QKV matrices, and ultimately our attention matrix will become bigger, so we make space for that as well. We take the dot product of the query value of with hat. Yeah, Q5 is hat, with the key value of every other token. You can already see 0.84 corresponds to a strong relation between cat and hat. Quick question, do we need to recalculate the bottom row down here? If we're applying a causal mask, no. We know that they're going to be eliminated to negative infinity, which gets converted into a 0 after applying a column-wise softmax. And we indeed apply that softmax across just the final column. That's the only part of this matrix that hasn't had the softmax applied to it. And the bottom row can, so that's all good. We don't need to recalculate any of the other columns. We then multiply each of these scalar dot product values by the value vectors, right? We sum them up. Only the final column changes to give us delta E5. That goes through the upward projection. And we use the output to modify the embedding of the word hat, and we keep cycling through. Yeah. I want to pause for a moment though. So consider this attention matrix. If we were to start processing long PDF files, say 1 million tokens long, or reasoning models, which chain together disgustingly long sequences of tokens, then we will end up with a 1 million by 1 million matrix. That is 10 to the 12 tera elements in that matrix, given a 1 million context window, as is the case with Gemini 2.5. And I believe that Llama 4, one of the iterations of Llama 4, claims a 10 million token context window. Am I asking you to recalculate 10 to the 12 elements every single time I want a new word? Absolutely not. When we calculated this new column, when we appended this new column with the new word, I had to take Q5 and I did two things. I took the dot product with K1 through to K5 and I multiplied it by V1 through to V5. Nothing else in the attention matrix changed. Nothing else. That means instead of recomputing 1 tera elements at each forward pass, all you should ever do, maybe not you personally, but all the developers that build these tools should ever do, is store your K values and your V values, your keys and your values, and only ever operate on those. And that is known as your KV cache. And you might have heard of this before. This enables us to avoid recomputing the entire attention matrix by instead storing prior vectors. This also raises an interesting distinction between the pre-filling phase and the auto-regression phase. During pre-fill, there are a huge number of operations, right? You've passed in your PDF, you've given it all the context. I've said, chat, here's a paper that I wrote, use my writing style so you don't use M dashes and use all those clauses that chat tends to bias towards. But all of these operations are highly parallelizable. There are a ton of tokens available to compute on. So prefill is typically a compute-bound process. And when you have a large model at the hundreds of billions of parameters scale, it makes sense to have your most expensive GPUs, your H100s and H200s, allocated to prefill. You might also hear prefill being referred to as ingestion because your model is ingesting a long sequence of tokens in parallel. Point is, expensive GPUs are more often than not allocated to prefill. Whereas the autoregression phase, also known as decoding, is when you've calculated the whole attention matrix so far based on your original input, and now you're just updating one column at a time. So you're not fully utilizing the compute of your GPU anymore. So this ends up being I/O bound. What I mean by I/O bound is that I can add more computational resources. I'm going to forgive Gert for this because of the kebabs. I can add more computational resources, more cores, more streaming processors, more threads. It's not going to help me, right? I'm limited by the constant movement of data between my cores and my memory, or HBM. So in many instances, using overpowered server class GPUs doesn't actually make much sense, right? So with sufficiently large models, I have seen industry use kind of two phases on this, right? Run two phases on different classes of GPUs. So we're already observing that, I don't know, it's not necessarily hardware, software co-design in the spirit of what neuromorphic engineers might do, but you can see how software is influencing the choice of GPUs to keep costs down. And that really just it covers the backbone of all modern language models, more or less, I don't know, all the operations that take place in a transformer. And then there is, of course, normalization between layers. And I've also ignored positional encodings.
But why not just store delta E's?
Why not store the
delta E's, why just not store those? Like, we don't need all the KV and KQ values.
Yeah, you need all the KQ values to be able to generate this new column. So bringing up positional encodings, I'm not going to go through it at a low level, but if you really care, just look up rotary positional encodings. There's plenty of really good tutorials out there on this. But given a sentence, we know that all of the words will influence the embeddings of all of the other words. But what if I rearranged this sentence without changing any of the words, right? So positional encodings aim to address this very problem. So not only does the surrounding context update every other token, but it's also a function of its position. So again, if you want to dig deeper into how the queen dancing might be distinguished from the dancing queen in an embedding space, rotary positional embeddings. And this is just one of many transformer architectures. And this is often what scares people away from the field. Also the number of GPUs that you need to be competitive. So let me try and perhaps simplify this. I'll try and distill the components that are common to almost every language model. Token mixing, that refers to the idea that information from your tokens are mixed with information from all other tokens. Multi-head attention dominates as the most common method. Architectures such as Llama and DeepSeek make slight modifications to reduce the cost of self-attention. We'll look into those when we get into more niche techniques. There's channel mixing. This refers to the idea that a model contains a bunch of general knowledge within it. And when you pass those tokens to your LLM, you're mixing numbers with an internet's wealth of tokens, and this is done by a ton of feed-forward layers. The final two ingredients in the generalized LLM recipe are largely to enable training ridiculously deep architectures and preserving gradient flow through deep models, normalization of your activations, and residual or skip connections. And these all come together to form a single block in an LLM. And these blocks are repeated many times on the order of tens to hundreds to really just do next token prediction. So with the 101 out of the way, I want to turn our attention to how we can make transformers efficient. Do we want a 5-minute break? All right, see you in 5. Okay, Johannes, come on. Come on. So, all right, so that's your canonical LLM that we've gone through. Yeah, with the 101 kind of sorted, let's turn our attention to how we can make these guys efficient. There are a disgusting number of okay. There are a lot of operations going on. How do we know which of these operations we should optimize to ensure maximal gain? Right? Don't want to target 1% of computation and try to optimize the hell out of that because it might be a bit of a waste. And there have been, yes.
There's a question in the chat.
Okay, are you able to moderate? Because I don't have the.
There's a great question in the chat.
It's just Johannes. Are you able to read the question, Paul?
What's being covered so far focuses on the operation during inference of LLMs only, or also for training?
No, I'm not going to go through that. Inference is, I mean, training is training, right? Training applies the chain rule to everything I described. Yeah.
Okay, yeah, good.
Yeah. I think most of the optimizations there are just how to distribute things across GPUs. Yeah. Gather roll-ups. Don't want to talk about that. So there have been a few studies, and I think most people agree on what needs to be optimized and when. So what you see here is a sweep of the number of gigaflops needed to run autoregression on a state-of-the-art open source model, QN 72 billion parameters. It's open source. The x-axis goes across the number of tokens in the KV cache, meaning that your attention matrix grows as you move further out on the x-axis. And there's one plot that shows the operations required for attention, and the other plot is for everything else, right? And that everything else is more or less dominated by all of the dense layers. In the short sequence length regime down here, sub 32K, the attention matrix doesn't contribute as much. In the long sequence length regime, which is where all modern LLMs have gone, context lengths of 100K and plus, the QK transpose operation, everything in that attention matrix blows up significantly. So you'll see that on the left-hand column, I'm really only talking about self-attention, right? I'm not giving much focus on the other operations because, I don't know, vector matrix multiplication has been around for a sufficiently longer time than self-attention. It's been hyper-optimized on GPUs. That territory is very much charted, and I have very little to enhance upon that. It can be modified. You can do things like run low precision ops, and induce some sparsity where it might make sense. But self-attention seems to be the key issue for those larger models. So we'll start by examining techniques that make self-attention more efficient without changing self-attention. I think this is kind of where shit gets hell niche and really interesting, to be honest. What I've listed are 4 techniques here. Really, it's actually just one technique, that is flash attention, which combines the first 3. We're going to step through it and make some space and use more convenient notation. So you'll recall the first step in our transformer processing, where we pass our embedding vectors into the QKV weights. We can represent that with a matrix multiply, or the QK transpose, right? And then how we did that column-wise softmax, let's just use this notation right here, softmax S, right? And finally, we had all of the elements of this matrix weighted by the value vectors V. And we can represent that with this expression, where O denotes some sort of output, and P is kind of an intermediate result that is a function of QKT and the softmax of that. So these are the three operations that we need to optimize for self-attention, and they will be running most likely on a GPU. And this is a very abstract view of a GPU, very hand-wavy, where you have multiple blocks, each with a bunch of threads that can process ops in parallel, and to execute a kernel, they'll fetch data that will go back to memory, and upon completing that kernel, they'll store the results via this data bus, which then goes to global memory, and this data access dominates the cost of most things on a single GPU. Now, running this matrix multiplication will require reading Q and K and storing S. Running this matrix multiplication requires the exact same kind of thing. It's got its own fetch and store. An unoptimized softmax operation can require 2 to 3 rounds of data movement back and forth. To understand why, let's go back to the original softmax equation. This is a bit weird. I'm going to spend an obscurely long amount of time on softmax, but just know that it's actually been a very fundamental thing in, I guess, both bottlenecking and enabling the performance of LLMs. So calculating the denominator requires stepping through every element in a vector and summing them up. It makes sense for that value to then be stored. Once that's done, you then step through each element in that same vector and you run the division over the cumulative sum, right? Then all of those values get stored. So we see 2 for loops. Is that a problem? Is it okay? We'll see. Now, a seemingly separate but actually tightly related issue is the numerical instability of softmax, right? The softmax is a normalizing operation, so the final values should be fine, right? They're normalized between 0 and 1. But if any element in your vector is somewhat large, then your intermediate results will indeed explode, right? Taking the exponent of each element will very likely mean getting a value that won't necessarily fit in full precision or half precision numerical format. So we see numerical instability as a result here. And the solution to this is known as the safe softmax. So take this exponential function as an example and say we have 3 values, A, B, and C in our vector listed on the x-axis. And then we'll get these 3 values, which I'll call A dash, B dash, and C dash. And I don't know, perhaps C dash has exploded. But what softmax is doing is dividing down these values like so, right? Now, let's say that I shift A, B, and C down. Specifically, I will subtract C from everything, right? And I end up with 3 new values, A double dash, B double dash, and C double dash, considerably smaller. We know that C double dash should just be 1, right? I take the softmax of them just like before. What is the point of all this? What's the relationship between the shifted softmax and the OG original softmax expression, right? It turns out they are equal. A linear shift of A, B, and C does not change the ratios that softmax calculates. And all the while, the maximum value here, C double dash, will only ever saturate at 1, right? So we can guarantee that our numerator never overflows. And all it took was taking our original softmax equation and subtracting the maximum element from all other elements. And it's the exact same result, right? So let's take our updated definition of the softmax, and we've solved numerical instability. That was pretty easy. But how many loops do we now need to implement this? So we're actually adding an extra loop to find the maximum element of the vector, right? You find the maximum, subtract it, sum the elements for a second loop, and then do the division for your third loop. So there are 3 loops. This could very easily lead to a stall in a pipeline. It could add an extra memory access step when we store and call the max value. Is this something that we can fix, right? And this leads us to the second optimization, the online softmax algorithm. I'm going to bring back the QK transpose dot product matrix that we've already seen. And we'll sub in some actual numbers into one of these columns, 3, 2, 5, 1. And recall that we're only applying softmax to individual columns here. So I'll get rid of all the other columns. And what we want is this. This is the safe softmax. We've subtracted 5 from every element. We're indexing into I. But again, I only know that 5 is the max value because I've already used my eyes, my brain to iterate through this vector, and I've said, yes, 5 is big, therefore subtract 5, right? Let's, on a computer, this is our third loop, right? So let's make this assumption that we only have access to one element at a time, indexing from 0. So let's initialize a few variables. We'll have one variable for the running maximum, right? One variable for some state variable. Ideally, this state variable might represent something that resembles my denominator of my safe softmax. We'll now expose the first element, 3. We can update the maximum value so far, also to 3. And this state variable, it ideally should be e raised to the power of 3. And with a safe softmax, we need to subtract the maximum value. We don't know that 5 is the global maximum here, though. All we have is 3 so far. That's all we've seen. They don't match, right? 3 minus 5, 3 minus 3, they don't match, but we'll fix that in a second. So let's move forward to the next step. We compare 3 against 2. We know that the maximum value does not change, and updating the denominator requires the addition of a new value, e to the 2 minus something. So we take the previous value of L and we add e to the power of 2 minus the local maximum that we have so far, 3. Now, if this was the end of our vector, we would be done. We'd have calculated our maximum value, which is correct, and the denominator of our safe softmax all in one single loop, but it's not. Now, as we move to the next element, the maximum value finally changes from 3 to 5, and this is where all hell breaks loose. This is the point at which our algorithm realizes, shit, I need to fix something, right? It identifies that you've made an error. Now, I can update L3, but it's wrong, right? It's wrong because L2 is wrong. We've been using the wrong maximum value this whole time. 3 minus 3 and 2 minus 3 really should be 3 minus 5 and 2 minus 5. It's really straightforward to fix on the fly, right? If I multiply L2 by some correction factor, fixed, right? That correction factor is very simply e raised to the power of the old maximum value, 3, minus the new maximum value, 5. In the event the maximum does not change, it would just be 3 minus 3 or 5 minus 5. Correction factor is 1. Nothing changes. But the point is, the denominators are now going to match. Go back and let that percolate for a moment. These two now match, e to the 3 minus 5, e to the 2 minus 5, with that 5 minus 5. Excellent. Without having to re-loop. And my final step looks something like this. Maximum is still 5. That doesn't change. L4 is updated. The correction factor does jack all. The final result of L4 is this. That perfectly matches the safe softmax denominator. So a little more generally, this is the equation where the correction factor is highlighted in red, where m sub I represents your current maximum, right? That's great. We've compressed 3 loops into 2 because you still have to go through your numerator, right? You've combined your finding your maximum and getting the denominator out in one loop. But it honestly feels like you're only solving a very tiny problem here, right? When you have these disgustingly large matrix multipliers on either side of the softmax, like, I don't know, we're missing the forest for the trees here. So the way that matrix multiplication is executed on GPUs is something like this, right? Say we expand out the QK transpose operation in practice, much larger matrices. The first operation might be allocated to one block. Don't expect you to be able to read that. It's just, Q1 times K1 plus Q2 times K4. It's just a 1 row by 1 column. In practice, you could fit a little bit more than this on a single block, more than just these 2 products. So you would partition your matrix across blocks. And let's run all of the QK operations across parallel blocks. So now say I wanted to fuse the softmax operation with QK transpose, with the goal of reducing how many times I transfer data to and from HBM, because that transfer is the killer. So the issue becomes the elements from my matrix, from my attention matrix, are now partitioned across blocks, this means that no single block has access to the global maximum value of any single column, right? In order to run the safe softmax algorithm. That's where flash attention comes in. It takes this idea of correction factors from online softmax and gives a way to fuse all of these three operations into those two loops from online softmax. The ultimate result is that you're able to achieve an almost 10x improvement in speed when running inference on what they showed was GPT-2. And this has now become the de facto implementation of attention. Let's not forget, right? We didn't modify the transformer. It's the same function, just hacked to make it an order of magnitude faster. It's a different sequence of steps.
Maximum gives you the smallest numbers, but you don't have to correct the maximum necessarily, right?
Yep.
Don't we know already have a good idea of what a distribution of values that we may expect? And so we just subtract the reasonable high value. You don't have to find the maximum at all, just keep it as a constant. And as long as there's a relatively large number that representative of the distribution, maybe some 90% percentile or something.
Yep.
And you just fix it.
And it may very well be the case that these closed source language models do just that. I couldn't comment because they're closed source. The open source models seem to do this. Why? It works, right? Maybe yeah. No, maybe that is, I'm not sure, right? I don't know if this is low hanging fruit or if it's targeting that 0.1% for very limited outcome benefit. Not sure if this has been studied in much detail in the context of large language LLMs. It's an idea. No, for sure. Yeah. Any other? Yeah. Question was, in a nutshell, why maximum? Why do we have to subtract the maximum? You can post hoc analyze what's the distribution of these values. Can't we find another optimum? The answer is yes.
That's the thing, maximum, you have some understanding of like what the distribution is like, and then you're subtracting. If you have a random, well, how do you choose that number, right? Like a big number, right? And it could just move very small values to even farther, or like even smaller.
Isn't a matter of
Yeah, maximum is, like.
Isn't a matter of preserving the dynamic range.
Yeah. Yeah, I mean, that is ultimately what matters the most, and making sure that the dynamic range doesn't fall into the outliers of floating point representations. And that gets a little tricky, right? Because, I don't know, different optimization or different backends are going to rely on different numerical formats, right? Brain float 16, half precision, mixed precision, etc. Like I don't think you want a technique that is kind of overfitting to any assumption about numerical format either. And it seems like this does a good enough job. But introducing Shashank to give the rest of the talk. Cool. So we didn't change anything except for the sequence of operations, right? It's still the same self-attention. Now let's turn our focus to things that perhaps supplement attention. And from here, I think things become a little more straightforward. You don't need to think so hard for these techniques. And I also mean supplementing attention in the most general sense, right? We'll cover modifications to self-attention, dense layer optimizations, and perhaps more high-level system layer optimizations here. It's not exhaustive, but rather a snapshot of what I personally think is most prevalent and most talked about out there right now. So the first attention modification I want to look at is KV cache compression. And there are a ton of ways to do it. We'll bring back our monster illustration of self-attention. Again, in multi-head attention, everything in this dashed box is parallelized a certain number of times, 96 times, 96 heads in GPT-3. So we have 96 QKV matrices, 96 of these attention matrices, and the outputs are all summed or concatenated together. This means that the amount of memory that our KV cache uses will also grow by a factor of 96. Even though the KV cache helps, right? the KV cache helps by removing quadratic memory complexity with linear complexity, but the scalar factor in front of that linear complexity is 100-ish, which is a lot, right? With limited VRAM. Now, a stereotypical model with, say, 64 layers will need 4 megabytes of KV cache per token. If you fill up an entire context window, let's say 100K tokens, then you need 40 gigabytes of KV cache. That will not fit in your VRAM if you've also got to store a model in there. Hell, the model alone won't fit into your VRAM. So let's clean up our illustration a little bit. There is a question in the chat that I'm now being alerted to.
It was a comment.
Ah, that's so professorial. I have a comment, not a question. It's beautiful. So we have this many heads.
Stuff was saying though. This max normalizing, subtracting it from megabyte is what slide rules.
Right. Yeah. I see this is a little tangential, but I don't know, perhaps in the neuromorphic live online learning crowd, there's a major parallel between the online softmax and real-time recurrent learning. It's the same outcome, just pitched a slightly different way so that you don't need to store your entire history in order to train a model with memory complexity that grows with your sequence length, right? I think these techniques are like really ripe for the picking in different domains. So KV cache compression, we have this many heads. Each head contains a unique query, key, and value matrix. And there's this technique called multi-query attention, where there is just a single key matrix and a single value matrix shared across all heads. So you can appreciate that this will absolutely reduce the amount of computation and memory, but it's also going to hurt accuracy quite a bit. So Llama 2 brought on grouped query attention, which is a bit of a middle ground between multi-head and the other one. Keys and queries are grouped between attention heads. In Llama, I think that each QV matrix is shared between 8 heads. So it's not as extreme as multi-query attention. I think Mistral also uses grouped query attention as that happy middle ground. If we were to do a bit of a hand-wavy comparison between these techniques, then multi-head attention works really well, but it uses a ton of memory. Multi-query attention is pretty memory efficient, but there's a big performance hit. Group query attention, it's fine, whatever. It doesn't excel at anything, whatever. But there is a trade-off, is the point. And that's a little bit of a shame. But then the team behind DeepSeek came up with something really quite useful. And while I'd say that most of DeepSeek's innovations were really thanks to low-level, closer to metal programming, I think this may really be the key architectural insight generated. So let's bring back our QKV operations from the GPT-3 architecture. I've updated the values to reflect DeepSeek v2. Instead of calculating the key value pairs directly, another linear layer is introduced. So we have a latent representation of KV. And that representation is then fed into the KV matrices with the argument that keys and values are inherently related to each other as they come from the same tokens. Sure, I agree. This, the way that I've shown you, doesn't solve anything though. We're just adding another linear layer. But instead, what DeepSeek did was fuse some of the matrix multipliers like so. So what we previously did was calculate the attention matrix using where is it? This equation here. We ended up with delta E, which we interpret as suggestions on how the original embeddings should be modified. But in order to modify the original embeddings, we had to project them upwards so that the dimensions all matched up, right? Which is kind of what that, yes, V followed by some other stuff is doing. And we fuse this upward projection with that value matrix. And you can trust me that your dimensionality all checks out. So we take the dot product between the queries projected into this latent space with what I guess is KV in latent space. That's their story, at least. And this latent KV is shared across all attention heads, right? So that's shared across all attention heads. And if we compare that against the other KV cache compression techniques, then it turns out that multi-head latent attention from DeepSeek dominates that memory performance trade-off. It's got high memory efficiency, and relative to the others, it's got the highest performance as well. So I'll be a little bit more tangible and swap out memory efficiency with real numbers. If we assume that the DeepSeek R1 architecture is being used, then we see a 57x reduction in memory usage and allegedly even get better performance on language modeling baselines. So that's pretty big. So to reduce, so that covers the most dominant attention modifications that are out there being deployed. Now, to reduce the amount of memory required, it's pretty well established that we are able to reduce the precision of model parameters or activations, and I've clumped this all into optimizations that you might apply to your dense layers or linear layers. So as an example, if you take a continuous signal, apply 3-bit quantization, then you're constrained to 8 permissible levels, 2 to the 3. Taking it to an extreme, this is what ternary quantization looks like, where values are constrained to 3 permissible levels. Microsoft, and then my own lab as well, have become pretty bullish on these low precision models, ternary parameters especially. We found that LLMs are impressively robust to these low precision regimes. And there are generally 2 possible ways to do quantization, with something in between. Post-training quantization just involves training a model in a floating point format, or just pulling whatever model off Hugging Face and then quantizing it at test time. We like post-training quantization because it's cheap. You don't even need to train a model if you're using someone else's model. The drawback is that the training process does not account for the quantization in the loss function, so you will take a performance hit as a result. On the other hand, you've got quantization-aware training, which fixes some of these. And this plot comes from Microsoft's BitNet paper, where we can see that as we reduce precision going from left to right on the x-axis, a post-quantized model, right, the janky process that's cheap, it's going to plummet in performance down towards, I guess, random chance. But quantization-aware training kind of blows past whatever Pareto optimal frontier here. Now, the way that this works is that it's honestly quite simple. During every forward pass, your weights are quantized. But the floating point weights are still stored, right? You quantize them for the forward pass to calculate an output loss, but the full precision values are just kind of chilling out in memory somewhere. When you run gradient descent, you apply your weight update to the full precision weights, or floating point weights more generally. You might also appreciate that quantization is a non-differentiable process, so ignore that during your backward pass. Hinton called it a straight-through estimator in 2011, so that's kind of stuck with everybody. Because you're passing straight through, you're estimating your gradient by generating a biased estimator that ignores non-differentiable ops. The benefits, primarily that you will get good performance, but it's less cheap. So as an example, this was a scaling law that we developed in one of our own ternary language models, specifically the matrix multiply free model that I'll talk about later. On the x-axis, we see the amount of flops being used. On the y-axis, the loss. And we've got various classes of models. So every pair is like a different scale. So a 370 million parameter ternary model against a transformer plus baseline, which is canonical transformer modeling. Then you've got 1.3 billion in this cluster and 2.7 billion in this cluster. Now, what's critical is that as these models get larger, this performance gap, not sure how easy it is to see, but this gap starts to converge, right? And we're comparing a ternary model against a BrainFloat 16 precision model. So as you go towards larger parameter regimes, it appears to be the case that the loss starts to converge. And if you can extrapolate and see that at some point, inshallah, these two things cross. So The con is that training isn't as cheap, but when you're doing 1 trillion parameter models, I don't think it's that big a deal, right? The clincher is more so that you're locking yourself into a particular precision. So if you do a ternary model and then the next best accelerator prefers 4-bit integers, you're screwed. So finally, something in between is fine-tuned quantization. Quite obvious, right? Take a floating point, full precision, half precision, whatever precision model, fine-tune the parameters either using full backprop or using some low-rank approximation of it. And this makes sense in theory, but to be honest, this is subjective now. I personally remain to be convinced of this yet. I think it will come, but people have developed these types of fine-tuned quantization models. Microsoft released an 8 billion parameter version of BitNet, or a ternary model on GitHub earlier this year, I think in March, which was fine-tuned. It didn't scale the same way something trained from scratch would have. I'm sure there are ways to kind of work your way around it, which effectively means there are still some things left to explore there for cheaper quantization. And also, these only apply to weights, right? My own experience with activation quantization has been pretty, I don't want to say depressing, but like a little bit. Going down to binary activations, say spiking neural nets, those have been difficult to train. I mean, we've done it, but they were really difficult to scale up to the point where I would not do it naively, right? It also, activation quantization, that is, even to 8-bit, 16-bit, seems to have a very hateful relationship with normalization layers. It struggles to cope with transcendental functions, exponentials, softmaxes, layer normalizations, RMS normalizations, which are everywhere in language models. So normalization is very sensitive to truncation errors in practice. So finally, I want to talk about system optimizations here. I mean, finally, for this subtopic, where we're far from final, and we're still going. I kind of think that these as like architecture agnostic, or that you can apply them to pretty much anything. There are some minor faults in my taxonomy if you nitpick, but I don't really care. We'll start with the mixture of experts. People have different interpretations. One of the more common ones is, let's train multiple models that are all experts at different things, and we'll choose the correct expert for a given input. I personally don't like that very much. I feel like MOE, mixture of experts, is asking a deeper question about computational efficiency because representations are distributed anyway. And that question is, how do we scale up to larger model sizes without scaling up inference compute? The answer, build a larger model, but don't use all of it at the same time, right? So attention is left untouched, but this output feed-forward layer is where mixture of experts kicks in. And zooming into this feed-forward layer, naively, you might have data coming in, passing through a dense layer with some residual. Let's throw in 4 of these operations and call them experts somewhat arbitrarily instead. How do we choose which of these experts to use? So that incoming data will go through what's called a router, where each expert has 1 neuron associated with it, each of which generates its own output, I guess, logit in a way. The router with the highest value basically wins. In this case, that's expert 1. And you can also consider this as a form of structured sparsity, where you can only load in the weights of the relevant block. And in practice, you'll see 16, 32, 64 experts with 1, 2, 4, 8, and so on active experts. And this can be implemented as the winning expert takes all. It could also be implemented as like a scalar summation of the confidence rating from the router to the output. An interesting thing to note is that during training, I am talking like a tiny bit about training, a naive implementation of doing this will lead to what's known as the load balancing problem, where certain experts will absolutely dominate everything else, right? If you reward one expert, it says, fuck yeah, I'm going to just be activated all the time. I don't really care about my other expert brothers and sisters, so it's all about me. Now, to address this, I think we could probably guess, right? You can inject noise, you could do some random sampling, combine your router with some random process, or you can actively pair your loss function, your cross entropy loss that tries to optimize your model to predict the next token. You can add some extra some extra term to it that penalizes your model for not engaging other experts. And there's an infinite number of ways that you might do that. In today's day and age, MOEs are used in more or less every single large-scale model. It's been the only way to successfully train 100 billion to trillion parameter scale models. Otherwise, you simply don't have enough GPUs in the world to do all of that. You've got to subdivide them down.
So are these experts training separate and separate data, or is it
No.
one single?
The latter.
Column, they're
The latter.
random pages in data?
The latter. Yeah, no. Yeah, they're cycling through the same iterations. I do not believe there is any guarantee that each expert is working on something different. You may find some level of correlation, and I think that people working on interpretability in ML are far more suited to answering this. But I don't know, I think my vibes are usually pretty on point, and my vibes are that it's just distributed representations, man. Yeah. Cool. Okay. So let's go to one of the other optimizations out there used in practice to accelerate language modeling. Now I'm not going through every single technique used, right? I'm going through specifically the ones that help with efficiency gains, right? MOE, by extension, does enable efficiency. Speculative decoding, the purpose of it is to increase your throughput as much as possible. And so the way that speculative decoding works is something like this. Let's take a small LLM, something kind of brittle, but perhaps it works well enough. We'll pass in our sentence to that small model. And because it's small, we can generate a lot of output tokens pretty quickly, right? So it generates the cat in the hat sat on the hostage negotiation, kind of blurring someone who wants to mute themselves.
Wait,
But
Diana? Wait, let me.
yeah, whoever that's talking about Diana wants to mute themselves. Sorry. I hope Diana as well. So the cat in the hat sat on the hostage negotiation. Let's take that output and pass it into our huge LLM, the actual LLM that we want to deploy, the one with the real brain. And it's going to take in all of those words. And remember, at the very start of this talk, I told you about how one sentence actually comes with many training examples, right? 8 words has 7 next word predictions in it, right? So this is much the same, right? The large model is going to generate a probability distribution over all of the newly rapidly generated tokens from the small model. And it might be the case that it identifies that hostage negotiation isn't very likely. Maybe there's another word after the cat in the hat sat on the that is more probable. And it's going to accept hat sat on the. And I guess it's going to, I don't have good animations here. It's going to accept everything else and then use its next token. So it's discarding some of this small model, the outputs of that small model, but it's able to generate 1, 2, 3, 4 tokens simultaneously, right? That, maybe not simultaneously, but far faster than running through 96 blocks with 96 attention heads would have done otherwise, right? I think that's pretty cool. The final system optimization I want to look at is knowledge distillation, which is probably the most broadly adopted technique in model compression. And I remember when I was a cute little naive PhD student and I was talking about the beauty and wonders of spiking neural nets. And this prof was like, why don't you just do knowledge distillation? And I was like, So I studied up on knowledge distillation. It's pretty good. He's right. No, I don't want to piss people off here, but it's good. Working together. So the idea is relatively straightforward. You take a big model, and you take a small model, right? The small model is the final compressed model that you might want to use in deployment. Perhaps you're trying to port ChatGPT over to your phone without internet. The goal is to make the small model to behave, the input-output relationship to behave identically to the large model. You feed data into both, you generate output logits from both of them, noting that even though both models may predict hat, right? Even though both models might predict hat, so I think these two distributions should have probably been swapped. In either case, assume this distribution is one where the small model sucks and the large model is good. Hostage negotiation should not be as large as it is there, but that's fine. You can interpolate. So in general, the small model might think that it's, okay, here's an example of something bad. The small model might think that there is a plausible chance for the cat to be inside of an aardvark. Don't know why. And you would usually take the KL divergence between these output distributions to update the small model. It's in practice actually going to be a weighted sum of the cross entropy loss, the actual ground truth, and the distance between the logits. So there's kind of like two loss terms that are, I guess, scaled accordingly based on how much you want to rely on your ground truth for training and how much you want to rely on knowledge distillation. One challenge in the era of OpenAI's closed models is that these logits aren't available to you. Only the tokens are. There are some nuances there if you go through the API. I think you can get, I don't know what the status is, but I think you can get up to the log probabilities of like a small handful of tokens, maybe the top 5 tokens, but you absolutely do not have the full distribution of all logits. But it turns out that there is still a functional way to do knowledge distillation, and DeepSeek did that with ChatGPT, where you just do teacher forcing in a way of the large model over into the small model. DeepSeek did this with ChatGPT. OpenAI got a bit pissed because it violates their usage terms of ChatGPT, but I don't know, maybe ChatGPT is violating the usage terms of everybody else's data. So, I mean, everyone loses. So with that being said, the last thing that I want to look at kind of leads into where the latter research talk part 2-ish type vibe will be. And that is all about modifying and replacing self-attention. So let's bring back the general architecture of LLMs. Sure, we could use attention as our token mixer, but there's nothing stopping us from RNNs or 1D convolutions. They can also be interpreted as token mixers. You know the history behind these things. Of course, we moved from RNNs over to attention because attention just works really damn well. So we've got our self-attention alternatives, full-length 1D convolutions, and our more time-varying options. Let's briefly look at 1D convolutions here. Let's say that we've got this world where we have this this one-dimensional sliding window. Sorry, it's 2 dimensions, but sliding across 1 dimension, therefore 1D convolution. And let's say that this first column of the green matrix represents the embedding of one of my tokens. This is the embedding of the next token. This is the embedding of the next token, so on and so forth. Now, a 1D convolution is going to take the Hadamard product of these 2 columns, right? And you get some target embedding. Maybe it represents the QK combo. Then we scan across again, and again, right? And this is used in Rakuv RWKV, if you're familiar with those more stateful dynamic models, and in Spike GPT, which my lab developed, and it's fine. I guess you could think of the pros as, you know, working not too badly on long-range tasks, right? Because in a way, your first and final token interact. That's why it's called a full-length 1D convolution, because that kernel is going to span the entire sequence of your input, right? And in this target for embedding, we see interaction between the first and final tokens, right? So you're able to get that relationship from the start to the end of your PDF file. The cons is that they're only interacting for kind of one step, if you will, one time step of that convolutional scan. It's also, it also means that the hidden state, I guess the number of target embeddings, that must expand for longer and longer sequence lengths. And inference complexity is also higher than that of linear RNNs. But convolutions have been so hyper optimized for GPUs, so much so to the point that when we use recurrent neural nets, the best way to train them seems to be by recasting RNNs into some sort of parallel scan algorithm, which implements a 1D conv. So even though modern efficient attention alternatives have pulled away from using 1D convs, they're still used in training long context RNNs. So, show of hands, who knows how the leaky integrate and fine neuron works? So can I just interpret as the raised hands as being in your lab? All right. So I want to look at RNNs as an alternative to self-attention by reference to spiking neurons. And I guess you'll kind of see the connection here. So the leaky integrate and fine neuron, very nice hand-wavy abstraction of biology, which preserves the spiking behavior of neurons. If I have this node, this neuron that's sufficiently excited over time, then it's going to trigger its own output spike with this kind of assumption or hope that the absence of firing means that there's no data movement from neuron to neuron, there's far less memory access if your hardware has been configured for it. So that's all well and good. It's really just a bilipid thin film membrane surrounded by some saline solution. And the inside, the intracellular medium is also some saline solution, just a bunch of ions inside and outside. If you have a conductor separated, if you have a pair of conductors separated by an insulator, that's just capacitive, right? But then there's also some highly nonlinear dynamical system of ion transfer between the inside and outside of this neuron. If you want to simplify it, if you want to make it computationally tractable at the deep learning scale, we'll just treat it as a linear expression, as Ohm's law, something resistive. So really, the leaky integrate and fine neuron is just a first-order low-pass filter. And what I like to say is that the neuroscientists stole from electrical engineers, so we want to steal back from them in order to make shit more efficient. At a high level, the dynamics look something like this, where the top plot shows you the input current injected into this RC circuit. The bottom plot shows you the voltage difference across this capacitor. That is, the difference between the inside and outside of the neuron. In a real biological neuron in your brain or whatever, something like -70 millivolts is where you'll expect to see it sitting. Here, this is an abstract view. I've simplified it down to just have a resting potential of 0 with some firing threshold of 1. Now, if I apply a current injection, then my membrane potential jumps up and then it exponentially relaxes back to its steady state value. That's our leak. If I have a current train, then you kind of see this riding on top of itself. This membrane potential just kind of accumulates. That's our integrate. When that membrane potential hits the threshold, that's our fire. At that point in time, this neuron is going to transmit a spike, often represented as a 1, rather than as nothing or a 0, to all of its downstream connected neurons. That's all well and good. How do we make use of it? That neuron can be represented in a recurrent fashion where you have a weighted input passed into a neuron. You decay that weighted input by some factor, beta. Beta sits between 0 and 1. So let's say that beta was 0.5, and that would mean that the membrane potential just gets halved at every step. That's exponential relaxation. So this is just a discretized solution for a continuous representation. Now, deep learning relies on acyclic computational graphs. So this recurrent neuron needs to be unrolled over time, going from left to right. We're moving forward through time, where the membrane potential, again, is just decayed by beta iteratively. And we need to preserve something learnable. So we have our learnable weight, I guess in this picture, it's just a weight scalar value with the knowledge that we have many of these neurons in parallel. So we end up with a weight matrix. These are the equations that govern it. But having said that, given that this leaky integrate and fine neuron is in a discrete acyclic computational graph, it's now compatible with all of the hacks that go with training deep learning models. That's all well and good. Some of you may be familiar with the non-differentiability crisis of spiking neurons. That is, if you threshold a value, or the membrane potential, then you're going to end up with a non-differentiable operator, right? You end up with a Dirac delta. When you plot that into the chain rule during backpropagation, it's going to null out all of your gradients. Therefore, no learning takes place. not so much a crisis anymore. I think all the quantized models and BitNet and all of those have shown us that we can indeed get away with approximate smoothed out gradients. So the backward pass very simply smooths it out. And what's interesting is that I've seen a lot of exotic activation functions coming up in modern language models, like you might have heard of SILU, SWIGLU, a bunch of weird shit that combines sigmoid and ReLU. Now, there is no sparsity in that. A typical model trained with ReLU, you might expect half of the activations to fall below the origin. Therefore, activations would be 0. This is not a spiking network, right? This is just a regular ReLUified network. But then in the era of these weird activations, we no longer have dynamic sparsity coming from anything that is not mixture of experts, right? Some people have tried to replace these with ReLU, but the problem, or the reason that we moved away from ReLU in LLMs was because too much information was dying, right? So we just have a smooth version of ReLU instead, where there is nothing really that's non-zero. There is nothing really that is 0, except for the origin. Some folk did the surrogate gradient thing, where they took a ReLU during the forward pass and applied the derivative of the SWIGLU or SILU activation on the backward pass, and that seemed to help boost performance while preserving the activation sparsity, which I thought was super interesting.
Just for everyone, the ReLU stands for?
Rectified linear unit. How embarrassing if I didn't know that.
Well,
yeah. Rectified linear unit, if your input exceeds the origin, pass the input. If it's below the origin, 0. So not much of an issue. Let's consider one layer of spiking neurons now. Cool, X goes in. The decay is now denoted with W1, W2, W3. At our first time step, I'm going to try and calculate the states of each of these neurons. So this is a vector of the 3 states, V1, V2, V3. I'm going to cast the decay values into this diagonal matrix, and we'll see why in a moment. That decay is multiplied by the current step of states to calculate the next step of states. And we, at the same time, add the current input from X. So when we do this vector matrix mult, the next time step state is going to be calculated by taking W1, multiplying it by the current state. Everything else gets nulled out. Likewise with V2, and likewise with V3. So in other words, V1 and V2 do not influence V3. Every state operation is quite localized in the spiking neural network world. We can represent this diagonal matrix as just a Hadamard product, right? That's a far more succinct way to express it. If we increment to another time step, we just keep doing this again and again. I want to kind of bring up a critical distinction from recurrent neural networks in the way that they were presented back in, I suppose, the 80s or so. The state, the hidden state of all of these neurons in recurrent neural nets, rather than spiking neural nets, are projected into some dense layer. They're cast through a nonlinearity, and then they're fed back to the inputs of these neurons. And so the equations are very similar, except we no longer have a diagonal matrix. Rather, we have a dense recurrent transition matrix with the nonlinearity applied to it, right? So if I can bring up this comparison between RNNs and SNNs, I think the key things to keep in mind is that canonical RNNs have this all-to-all recurrence, that is, all neurons influence all other neurons. It feels like a pretty strong token mixer in a way if everything is influencing everything else. But they're also nonlinear through time, right? There's always a nonlinearity through layers, but I'm also saying that there's a nonlinearity when you update the state of these neurons. Whereas with spiking neural nets, you have one-to-one recurrence. Every neuron state only influences its own state. And it's also linear through time. That's important because linearity through time means you can get a closed form analytical solution for these equations, so you can train things much, much faster. That linearity is broken the moment you add a reset mechanism. Biological neurons like to go through this thing called hyperpolarization, where they get pretty angsty after they've fired and they don't want to fire for some period of time after that initial action potential. We just model it using some reset. That breaks linearity through time. And that should be ringing some bells of whether or not we should really be applying that. It's also a local state update, which is considerably cheaper. So we've trained spiking neural nets to do language modeling, and I'll talk more about that in the second session. But I want to, I guess, be as transparent as I can with some of the pain points of spiking neural nets. In software, this nonlinearity through time due to reset breaks parallelism. They also have considerably weak representational capacity in the way that we train them right now, because activations are squeezed down to 0, 1. And all of the deep learning things that we've learned relies on amplitudes of activations. We don't really account for sequences and patterns and things that the brain probably definitely does. In hardware, and I am referring specifically to large-scale modeling of, I don't know, things that are competitive with deep learning. In hardware, communication cost almost always dominates, I guess, computation. And so there's a bit of a question of how necessary single-bit spikes are. Maybe it's really just the sparsity we care about. Doesn't cost much to add a few extra bits and transmit a little bit of an amplitude and working with that. In addition, these are dynamical workloads. You do not know until you have access to your data as to which neurons are going to be triggering. Procedural workloads, something deterministic, is very easy to design around. Asynchronous design is also very hard. So what you've just implicitly learned are state space models, right? Without actually telling you what state space models necessarily are. They're just a form of linear recurrent models, linear through time. You can apply whatever the hell nonlinearity you want when traversing between layers, but when you go through time, it's all linear. If you're not feeling completely broken, I'll go through my lab's results on things that have worked and things that haven't worked in the next session. But with that being said, I think you've all kind of got this basic background of everything I wanted you to know so that you can kind of go home and go to sleep or stick around if you hate yourselves enough for the research part of my talk. So with that, thanks. Go chill.
Wow, perfect timing. Question, we have plenty of time for questions.
Yeah. What do you want, Vikram?
So, in like going back to the very last point, where you're like, oh, sequences are important for the brain. So my question is, in the stage in an LLM, where we have to, take this, compute these changes in embedding, so you have high dimensional computations. For ReLNets, is obvious to me that, you have these vectors with floating points in them. With SNNs, you either have rate coded unit, which you can probably treat like a rel and do the same thing. But how do you compute with like sequences?
I'm not sure I understand. I don't understand, sorry.
Okay, so with ReLU units.
Are you saying that spiking neurons have different interpretations? You have possible rates in the neurons. How can you compute something as rich as language using individual spikes that are occurring over time? Or did I miss your point? No. Yeah.
So let's say I represent a vector with either floating point entries, or I represent a vector elements with sequences. Yeah. With ReLU neuron, I have like a stereotypical vector which has, it's a list of numbers. You can do addition, subtraction, whatever you want. With sequences, how do you do that in essence?
So is there anything stopping you from doing additions and subtractions and whatever you want with sequences through time and space? So let's see.
Yeah.
It's hard to answer a question I don't understand.
Like sequence A minus sequence B, like how do you?
Oh, right. Oh, okay. Gotcha. So your question gets at if you have a sequence with data distributed over time, gotcha. How can some information at a later timestamp back reference information at an earlier timestamp? Now, this is a very there is such a rich, comprehensive answer that I could spend like 7 fucking hours on explaining to you. The TLDR is this, because I am going to go into this in a lot of detail in 30 minutes with all the research that we've been doing. You are able to reformulate the self-attention operations as a recurrent operation. You just have to preserve a ton of states, right? Does that make sense? Probably not. If, on the other hand, you're constraining a recurrent network to not expand memory through time, the most obvious thing coming from LSTMs in 96 is to forget shit, right? You remove something from that constrained memory, you make space for something new. And I'll go into that in a bit more detail because that's what state-of-the-art state-space models use right now. On the other hand, you've got Mamba, one of the most famous state space models that kind of put SSMs on the map of a lot of the deep learning people. They do what's called state expansion, right? If you have constrained memory, let's at least project it upwards to get a bit more space in there, right? And inshallah, you're able to store a few values. Shashank pays attention when you say this shit. You're able to store some information from later in time, and hopefully you could combine that with forget gates to be able to just have a bit of a richer understanding of things that dynamically vary through time. Yeah. That's a good question.
Not with long, short.
Yeah, Gert's picking at me for not defining acronyms. Yeah. I'll spend a ton like the next thing on exactly this, how to enable good long-range memory performance with RNNs. Yeah. Any other questions before I lie down for like 25 minutes? Yeah. I just need all right. I thought you said, do you need a room to lie down? I was like, wow, kebab and a room? This is sick.
Questions? And the Zoomers are also more than welcome to ask questions. It looks like everybody is.
Everyone understands so well. Is there a question up there?
Isn't that spiking maps for top tier of the series of spikes that encode information? I'm not very familiar with this side of models. I was wondering what kind of, you probably have to do some kind of rate encoding or something, right? Like, how do you actually extract information from a sequence of spikes that is different from the amplitudes that we get from these other deep learning movements that are non-spiking?
Truth be told, I don't think too hard about like what type of encoding I try to avoid enforcing any sort of encoding scheme on my spiking neurons, right? I'll like really consider, okay, what's my input? Some people are constrained to having spikes at the input, in which case, then sure, you would need to convert some embedding into a sequence of spikes. But granted, that embedding process is nothing compared to the rest of your model. Therefore, if I can just preserve that original full precision representation or half precision representation of my embedding, I'll do that. I will not encode it in any format. I would ideally just let backpropagation do its thing to let every neuron learn when it should spike. And then at the output, maybe we can default back to using floating point representations, and just some readout layer is acceptable. And I've seen a lot of CVPR and fancy papers that do these things with like 3-layer networks. That is, you've got one layer of spiking and then start and end a non-spiking. And at that point, it's like, what's the point? Who cares, right? In this case, it feels like it could make a little more sense because, like 0.5% of your model is not spiking. As long as you have something cheaper, that's ultimately what I personally care about. Now, this answer is heavily skewed on this assumption that we're using modern gradient descent, surrogate gradient descent and all that on SNNs in this acyclical computational graph way. For people listening on Zoom, Johannes is talking again. Say it again.
The premise of SNNs is often, like as you said, like people are assuming that there's a lot of sparsity for energy and so on. But if you have like this sort of rate encoding, you also need more spikes to represent the same amount of information. So I was just wondering, like practically for models that use sort of similar performance, how is the compute trade-off? Like running a similarly capable spiking transformer versus no spiking transformer, does it actually pan out the way, or is it actually less than some more less?
It's a really good question. I'm going to give you the most cynical answer, right? Is anyone in here like worked on spiking transformers. Thank God. I think it's, I don't want to say bullshit, but like I almost want to say that it's solving the wrong problem, right? A lot of these models are taking dense layers and making them spiking while leaving these gigantic attention ops in full precision. Sure, good on them for being capable of proving that, you know, part of your ops can be sparse, can be spiking, but to call them purely spiking is, I don't know, it's very falsifiable, I think. So I don't think the efficiency gain is substantial there. It, again, in the current way we do things, it makes a lot more sense just to relify your networks. I think that there's a lot of low-hanging fruit in enabling neurons to interpret spikes in a fundamentally different way to what us SNN deep learning people have done, and perhaps look a little closer to what the neuroscientists are doing, be it oscillations, spike patterns, spike sequences, not even like latency delay. I don't want to say these things, but just the more richer ways to represent information, right? If you have like one neuron and you add a little bit of extra time, then you're going to exponentiate the possible ways you can represent information if you distribute information through patterns and times, and maybe you get a phase change if two neurons have different, like relative different spike timing in the way that STDP showed, right? There's a lot of stuff that hasn't been done, and it'd be really sick to go down that road.
In fact, talking about attention, a neuron that is a coincidence detector.
Yeah.
Will detect
Exactly that.
this multiplication of your occurring your key.
That's a cool interpretation. Yeah.
So this is a little bit into the quantization question. So I guess more with the fine-tuned quantization. So is there probably a way in which we can decide where to put more precision into, either during training or if you do like a Bayesian optimization or something like that?
Damn. Yeah, I don't think we have anything all that principled, to be honest.
So I guess you can keep bulk of the network binary, ternary spiking, but then some neurons or ways that are super critical.
There's nothing. Sorry, I just went for a sit down. Yeah, no, that's totally right. There's, if it makes sense, and if you have the hardware there, then do it, right? If deeper layers just so happen to be sparser than earlier layers, then maybe they can tolerate that deeper quantization as well. And there is nothing principled about the way that we do fine-tuned quantization. Like I've got this idea, it's probably already been done, to be honest, but using low rank approximation to do that fine-tuning quantization process. People have already done knowledge distillation to fine-tune.
I mean, that works, so that's already a big deal, right?
It works, but none of these, I don't think any of these work as, they don't really light a candle to training from scratch. Bridging that gap would be really cool.
So this is great. Now we're getting into the nitty-gritty details
weeds
of how these things work.
Yes.
So there's a good segue to the second, the lecture, but let's give Chase a little break. So
I'm
first of all,
not tired.
Okay, so 20 minutes and then we can continue. Is 20 minutes enough?
Yeah.
We'll have
20 minutes, good man.
Yeah, you need.
Foot rub? Or oh no, that's not an offer. Okay. No, good man, thank you. Oh, yeah.